Thanks, everyone. We are glad to have you here today. We're going to be discussing our stealth breakthrough regarding Intel AMT. We hope that you find this talk informative and useful. Unfortunately, Alexander and Maxim could not be here with us today. But my name is Donald Anderson, and I will be their replacement. I work at Embedi, and with me today is my colleague, Dmitry.
Hello, everyone. My name is Dmitry Evdokimov. I'm the Chief Technical Officer at Embedi. My interest is code analysis, reverse engineering, and automation with tasks, mostly in Python. I'm also maintain Python arsenal for reverse engineering project.
Okay, and at any point today or during this presentation, if you have a question, feel free to ask us. We have a Twitter set up with the hashtag #AskAboutIntelAMT, and our team is standing by waiting to answer any of your Intel AMT related questions. So, today's agenda will have us start off by breaking down the basics of Intel AMT before getting into some of our more interesting newer findings. We're going to start off today by taking a look at the architecture of an Intel 64 system. So here, this is a typical Intel 64 desktop laptop system architecture. Intel CPU is definitely the main execution environment. However, it's not the only one. There is also an additional chipset which has integrated controllers and subsystems which support peripheral devices and some other system functions. One of these subsystems is the Intel Management Engine, or Intel ME, which we are going to be speaking a lot of. It's an isolated, stealthy, and the most powerful within the execution environment. And when we say powerful, we're simply referring to the capabilities that this system has. It's capable of controlling very critical systems. The common SPI flash contents are divided into regions. The main region are the flash descriptors containing offsets and sizes of other regions, and it's able to access permissions to them. Each user of the flash could find its region, and for security purposes, wouldn't have access to other regions. Excuse me. So the next region belongs to the specific user of the flash. Oh, there we go. Go down. Thanks. The gigabit Ethernet region exists for the network adapter and stores the configuration for its MAC address. The next region is designed for the Intel ME subsystem. It stores the Intel ME firmware. The ACPI EC region has appeared since Skylark architecture, though we've never seen the latter. So the ACPI EC firmware blob is included into the last region, the BIOS. Any program code that is running on the system is executed in one of these CPU protection rings. In ring 3, you see, you have user applications that have the least amount of privileges in the system. At ring -2, we find the system management mode, or SMM, which is the most privileged within the CPU. Its code is located in a hidden SM RAM, which is not seen at any other level before it. However, we were able to gain access to the most powerful execution environment. That is the Intel ME, as I mentioned before, located in ring -3. It has even more available access capabilities and memory isolation techniques. So now we are going to go more into depth here with the Intel ME AMT architecture. Besides the management energy memory control unit, this subsystem consists of Mac level controller, host embedded controller interface, unified memory architecture and firmware, which is stored in the common SPI flash alongside the BIOS. This subsystem is generally thought of as the most privileged and hidden execution environment, and there are a few reasons for that. For one, the unified memory architecture is hidden from the CPU. Additionally, it has full access to DRAM and out-of-band access to network interface. The most interesting thing is that Intel ME still works and accessible even if the device is turned off, as long as the device is still plugged into an outlet. This subsystem is present on any Intel-based system since 2010. However, its name varies depending on the platform type, though. Year by year, the interest of researching Intel ME has increased. The main problems with reverse engineering this technology and its firmware are as followed. One, Intel ME firmware code modules use syslab functions implemented in the boot code inside ME ROM. Therefore, it is difficult sometimes to understand the function behavior without the knowledge of what syslab functions are called. Fortunately, ROM images can be found in the debug versions of ME firmware. Two, a certain part of Intel ME firmware code modules are compressed using the Huffman algorithm, but the decompression dictionary is unknown, so the decoding is not easy. Though not impossible, the dictionaries for 6 to 10 versions were reconstructed. Number three, one of the most well-known problems is the undocumented communication protocol. However, the details of this protocol can be reverse engineered. Four, the ME UMA library in DRAM is inaccessible for the main CPU. And then finally, Open Source Society has created a heading to disable Intel ME subsystem, but this is quite difficult. A method has already been presented to restrict the subsystem's functionality by cutting the unnecessary firmware components. If you're interested in reverse engineering the Intel ME firmware, you will need a disassembler and a few scripts, which you see here. So what we're going to do is we're going to put this presentation on our website. So don't worry about trying to copy everything down. So everything is going to be there if you want to go back and check later. So Intel ME architecture and the security model understanding is an extremely broad theme. So again, this will be on our website, so you could go ahead and take a look. So you could use these links to gain more information regarding that. Now onto the Intel ME firmware components. To understand this segment of the presentation, we really needed to provide you with some of the basics of the MT firmware architecture. The code is divided into modules, and depending on the system, the code module list varies. There are the basic code modules such as the bring up and kernel modules in every firmware version. Each of these modules implement the specific Intel technology. For example, Intel AMT. There are 3 firmware types. Ignition firmware, which is actually only available for the ME version 6 and is the minimal firmware size and contents. Then we have the 1.5 megabyte firmware, which has incomplete module contents. And then lastly, the 5 megabyte firmware, has the full firmware contents. Onto the Intel AMT architecture. It is implemented as code module inside Intel ME firmware. The technology itself is meant for remote control and administration of computer systems. So it allows powering on and off, resetting the system, and accessing BIOS setup through serial over LAN. It also allows getting the information about the system hardware through the web interface. Also booting the system from the custom boot image file. Also acquiring the full control of the monitor, keyboard, and mouse of the system. Any of these features requires only the target system to be plugged in and to have the official AMT support. Regarding the vPro brand, these capabilities don't necessarily depend on an operating system of target. Moreover, it could be used to delete or reinstall it. There are several ways to access the Intel AMT features. Remote access is available through the wired or wireless network interfaces. Starting from certain versions, messages received on a wired LAN interface and addressed to certain ports are intercepted by management engine prior to reaching the OS NetSec. Messages received on wireless interface go to the host wireless driver. The driver detects the destination port and sends the message to Intel AMT. Various local applications are able to access the Intel AMT features the same way network applications do, like WS management over SOAP over HTTP. And here are the most well-known network ports that are used by the remote administrator to access the AMT system.
So, thank you, Don. I will take the floor at this point. Move on to the next section of our presentation. And let's have a look at the possibility of unauthorized remote access to Intel AMT system. At first things to do is to look from a user's point of view at how the things are arranged. When users access the Intel AMT web browser via the 16992 port, they are referred to a logon page and a challenge with standard authentication request. So let's use Mint proxy. Now with help of proxy server, let's analyze what is actually happening in more details. As for RFC 2617, digest unification, the first request gets a response with 401 code, which means unauthorized. It's OK. Then given a correct name and password, the server accepts one as a legitimate user. When given incorrect username or password, server doesn't accept one. This kind of behavior is not surprising at all. On this slide you can see a network traffic of successful attempt. So nothing extraordinary has happened during the authentication process, but the detailed look at the snippet packets gives us a clue of what to look for in ME firmware. It is authorization header field names. It is a bunch of strings like username, real name, response, nonce, which string can be used for searching through firmware and pinpoint the very code that is responsible for the digest authentication. For purpose of reverse engineering, the Intel ME firmware, we will be using the IDA Pro disassembler and a special loader script. This plugin was written in Python and it adds to ME format. It's a support ME format in IDA disassembler. It should be work for all firmware versions prior to 10. So after our talk, you can download this plugin and use in your own project. And after the loader completes parsing or otherwise processing, the firmware will have a nice and clean look onto the present code and data. You can see on this slide. So a quick search for the strings like username, cnons, real name, etc. Provides us with the exact strings within the next tag module. As we can see, they are all cross-referred from one particular function. This function is responsible for processing authorization header fields and their overall digest authentication. After a careful examination of the function code, we found an interesting bug. The exact place of that bug is in the final comparison of the provided response and the computed response. Two values were tested against each other to see if they match, but the actual number of bytes to be tested was taken from the user-provided response. Thus, if one provides an empty response string, string comparison function returns 0. As the number of bytes to be compared is 0, and 0 means successful authorization. It's all bug. So, let's repeat our previous experiment, but with local proxy. In order to exploit the newly found vulnerability, one can use a midterm proxy tool with a simple script that blanks the response field in the authorization head of outgoing request. It's a very simple script which has a small size, about 10 lines of code. Need configure web browser. The web browser is configured to access the network through the local proxy at 8080 port. The password we have just typed in obviously incorrect because the Intel AMT doesn't allow password shorter than 8 characters, but we will give it a try. So, for first request, we have the same results as previous our experiment, but for then, voila, take we have a code 200, which means successful authorization, and please take a note on the value of the response field of the authorization header. It's empty. So, attacker is now authenticated as a legitimate system admin. It has a full access to a variety of Intel AMT controls. He can do absolutely everything without knowledge of password. We checked this vulnerability on other Intel AMT versions from older to new ones. To check them, we simply use a local proxy without any reverse engineering. After that, we reported this vulnerability to Intel, and then Intel offered us to participate in their private bug bounty program on HackerOne. And we were given $10,000 award. So, as must have understood, it's a authentication bypass vulnerability, which was later to know as CV2070-5689. This vulnerability originally discovered in beginning on this year, in middle of February. So, for successful exploitation, for attacker only need open AMT port. It's, for example, 16992 port. Of course, this system should base it on Intel CPU and chipset and have a valid BIOS and Intel ME firmware. It all is required. This system can run on a Linux operation system or Windows, it doesn't matter. Only Mac not affected because this code is absented on Mac computers. So the general idea, the idea is attackers' possibilities and AMT capabilities as the same things. So, Don, need your help.
Okay, and how about the impact? According to Shodan, on May 2nd, there were 6,378 available IPs with Intel AMT. However, it should be taken into consideration that Shodan's data covers only the internet, while a good deal of Intel AMTs are used on corporate networks. These corporate AMTs can easily be used by an attacker who has connected to a network. The most impacted industries, as we see here, are telecom providers and universities. It turned out that this vulnerability had affected ICS. For instance, Siemens Industrial Computers, based on the Intel chipset, were susceptible to it. In other words, not only enterprises and public organizations, but also critical facilities may also be affected by the vulnerability exploitation. So we have a demo here that we're going to show you.
Yeah, we want to show some demo. So, first, configure a local proxy in browser on NT80 port. And run Metal proxy 2 at this port. Try to log in. It's incorrect password, and we can't log in. But then we input a correct password. It's a very long password, and a successful attempt. Then we run our Metal proxy tool with our scripts, and repeat our attempt with password 1 symbol. That's all. We have a successful exploitation. This is the second demo. So, let's go next.
Okay. And after our blog post went public, Tenable, a network security company, was able to rediscover our vulnerability despite not having access to any of the technical details of this vulnerability. And then after we released the technical details, the security community developed many useful tools and scripts developed specifically for this vulnerability. One of the most interesting tools being honeypots. The existence of these honeypots now makes it very difficult to understand how many Intel AMT systems are truly accessible from the internet. Now, how can we eliminate this vulnerability? Well, Intel created a patch for this vulnerability and provided it to all affected OEM vendors. Following this, all affected OEM vendors created new firmware, which is now available for users to download. Because this vulnerability exists at the firmware level, you personally have to update it, so it's not going to happen automatically. So how many of you have actually updated, or excuse me, installed this patch? So, yeah. So now we're going to begin to talk about our research, which we haven't released yet, so you'll be hearing it for the first time just now.
Thank you, Don. So, it's all good and well, but it is possible if Intel AMT is activated. Yes? So, we wondered, if is it possible for attacker to spread out the coverage of this vulnerability and Intel AMT itself to their own goals. As you know, Intel AMT is part of vPro brand. First of all, we want to understand how exactly the non-vPro system differs from a vPro system. So, non-vPro system is based on ZHBP type chipset. It's more cheap system. When vPro system based on Q-type chipset from Intel is more expensive. So we checked that non-vPro and vPro system may have absolutely similar Intel EMU firmware images. So Intel AMT implementation is often present on a non-vPro system. There is Intel AMT code in all 5 megabytes firmware versions. It turns out that main difference is a MapX module and some options in BIOS setup. It's a BIOS model that uses HECI to configure the Intel AMT. However, maybe there are some hardware restrictions, and how can we interact with it and make it work? The HECI interface seems to be a useful communication channel with Intel ME. It could be used, for example, it could be used for in debugging to gain the status of Intel ME or retrieve some other information, and for many other interesting things. Unfortunately, it's pity the command system is not public. A little bit about HECI. HECI interface is a bunch of registers set in PCI, SFG, and WMIO. The message should be sent through the cycle buffer in WMIO. The message should contain a command. After the message is sent to Intel ME, the acknowledged message is to be responded. There is a driver designed for this purpose in the system. You can see this driver in Device Manager. It is this driver that maintains the communication with Intel ME. The message protocol itself is based on DCMI-HI protocol. To send a message, you need to know the GUID of the specific client you want to communicate with. There are some known clients with a certain set of capabilities. In our case, to configure the Intel AMT, the AMT-HI clients must be used. So, the format of message with command varies depending on the HECI client you are communicating with. So, for the AMT-H clients, the following format is used. As you can see, the message have the group ID field, meaning the command group identifier. Each group has a specific set of commands. To configure the Intel AMT, the 12 group ID must be used. So, after reverse engineering, we found commands for AMT activation and deactivation. The following commands must be sent one by one to configure the AMT. After sending the message, don't forget to receive the acknowledgement. Very important moment. User interface for enabling and disabling AMT is absent on Intel non-vPro system. That means user can't disable Intel AMT after activation on non-vPro system. So it will be persistent activated Intel AMT on system. After reverse engineering, we found a command for deactivation Intel AMT through HECI interface. It's only one command, AMT unprovision, and after that command need a reboot system. But in one interesting moment, not need to acknowledge about password for activated Intel AMT. You can just deactivate Intel AMT, then activate and set up your password. So, as a proof of concept, we create a tool to activate and deactivate the Intel AMT on the system, both vPro and non-vPro. The activator consists from two drivers and one user space application. For using it, you need admin privileges. So, the AMT activator was tested on the following system, and we open source code of this tool, and you can use on your choice this code. So this code contains an activation and deactivation command through HCI interface. So now I want to show you a demo. I have some problem. So first system is Windows 10. It's a computer for attacker, and now attacker tried to connect to a remote system. It will be known vPro system without activated Intel AMT. So then attacker then we move to System 2 and run our tool. Especially for demonstration, we also show how we delete Intel Management Engine interface driver for demonstration that our tool not need with a standard driver in your system. Delete the driver. Driver is absent. Open our tool and run with enable argument. The log says that's all fine. AMT successful activated and the IP address was assigned. Now we come back to first system and try our attempt. Try to connect to Intel AMT to system 2. Of course, because attacker run AMT activator, he know username and correct password. Yeah, we see a web interface of Intel AMT. So Intel AMT successful run on a non-vPro system. You can see that is a gigabyte non-vPro system. It's chipset GAH97. So, it's all. Current version of AMT activator has some limitation. For example, these versions are only for Windows, but can be ported to Linux, of course. And we use own kernel drivers, and you make implementation which based on standard Intel Management Interface driver. So it's possible. So done.
So perhaps now you guys are thinking about possibility of Intel AMT being used in malware. As for malicious code using Intel AMT, it's worth noting that first, Legbakor researchers have already come up with this idea in their research. Second, quite recently, Platinum, a malicious program, has been detected in the wild. Platinum uses Intel AMT SOL to secretly communicate with the CNC. In both cases, the malware does not use a vulnerability in the Intel AMT. Contrary to it, the malware uses only common Intel AMT SOL capabilities to keep communication stealthy and evade security applications. As Microsoft stated, this channel works independently of the operating system, rendering any communication over it invisible to firewall and network monitoring applications running on the host device. So the combination of the kind is not really fiction, but fact. So on here. So now how can we mitigate this problem? Well, the community suggests several methods. However, none of these techniques are really perfect. In some of these cases, the attacker has a countermeasure for your mitigation technique. If you are a company that uses Intel AMT frequently or even infrequently in your corporate network, you simply just can't block this port on the network firewall because you need it. And then you can always use Meat Cleaner to remove this functionality. However, this is dangerous and can break your system.
So, we didn't stop here, it went on. We had the question to be answered. What can a potential attacker do if a system has a 1.5 megabyte firmware without Intel AMT implementation? This part of our research is progress now, and so far we have a following result. The obvious way to swap the 1.5 megabyte firmware image to 5 megabyte firmware image on the system is to use the SPI flash hardware programmer. This allows to bypass the flash regions locks. So some systems have SPI flash regions unlocked, so this opens the way to do the same from software. The administration privileges are needed in case you need use a kernel driver or, for example, exploit some local privilege installation vulnerability in BIOS, in SMM mode. So, we have a successful attempt made it on gigabyte system. So, that's all now, while.
So what can an attacker do by using Intel AMT? Well, this table demonstrates what is possible with each chipset series. As you can see, there are still some question marks out there, and this is because there are just so many systems and so many different configurations. For us, this is still a work in progress. So we're going to go ahead and ask you guys, if you could help us out in this great endeavor, it would be fantastic. Now, this slide is a demonstration of how an attacker would maneuver through your system. First, the attacker will check to see if your system has AMT enabled. And if you do, and it's not patched, then the attacker can just go right ahead with the Intel AMT exploit. However, if it is patched, the attacker can attempt to activate AMT or increase the size of the firmware and then activate AMT to use your Intel AMT functionality. The thing is, because Intel ME is ring -3 and occurs at the lowest level, like we said before, people have to patch this firmware themselves. And obviously this is going to be rare. So what this means is that this vulnerability will exist for a very long time. Now, just for some of our final takeaways, we've established today how easy it is for an attacker to exploit our vulnerability in AMT web server. We also showed you how an attacker can activate and deactivate Intel AMT on vPro and non-vPro systems through undocumented features. And finally, we demonstrated how it is possible to swap firmware images from 1.5 megabytes to 5 megabytes for the goal of adding Intel AMT system. So we hope that our research has shed light and brought awareness to the security issues that ring -3 faces. So thank you for your attention today, and don't forget to use the hashtag #AskAboutIntelAMT for questions throughout the day. Thank you. Nice job. Very nice.
Yeah.